Chapter 2, Section 3 discusses measuring. Whenever we're doing measurements, we want to make sure that they are both accurate and precise. Now, accurate means that our measurement is going to be very close to the true value or the accepted value. Whereas precision deals with how closely several measurements are to one another. Now, it is possible to be precise without being accurate. For instance, if you look at the diagram here, you can see that all three of the darts are thrown very close together, so they're very precise, but none of them are very close to the actual target, which would make it accurate. So when at all possible, we try to ensure that our measurements are both accurate and precise. And an easy way to do that is to simply make sure that you're using the correct equipment when measuring. If you're dealing with very small volumes, for instance, you don't want to use a giant beaker. It's probably a better choice to use a smaller graduated cylinder or perhaps even a burette. Whenever doing calculations in our science class, you should be using the appropriate significant figures. So you shouldn't be asking, how many decimal places should I take this answer to? Your answers should always be in significant figures. So a significant figure is any digit that's known with certainty plus one final digit. Now, anything that's not a zero is always going to be significant. So what we're going to need to learn are some rules for the zeros, and those are listed on page 59 in your textbook. This is a summary of those rules. So the first one tells us that when we have a zero that is sandwiched in between non-zero digits, they will be significant. So for instance, in this example here, 40.7. The 4 and the 7 are significant, and the 0, because it is sandwiched in between those two non-zero values, will also be significant. So this answer, or this number, has 3 significant figures. The second one tells us that any zeros that come in front of non-zero digits are not significant. So in this value where you've got 0.009587, this only has 4 significant figures, these last 4 here. These zeros out in front are just considered to be placeholders. The third one tells us that at the end of a number and to the right of a decimal, zeros will be significant. So this value here, 85.00, this has 4 significant figures. This is telling us that we can be as precise as to measure all the way to the hundredths place. If it were just 85.0, well then we would only be able to be as precise as to measure to the tenths place. And that would have 3 significant figures instead. Number 4, and the last one here, is that any zeros that come at the end of a number with no decimal may or may not be significant. So for instance, 2,000. Okay, there is no decimal place here. We know for a fact that the 2 is going to be significant. Then this 0 might be, this 0 might be, or this 0 might be. So we would say that this has 1 to 4 significant figures. Now, as soon as you put a decimal point here, that will make all of these zeros significant. So this is telling us that all 4 of these digits here are going to be significant, so this has 4 significant figures. There are also exact numbers as opposed to measurements, so not everything we do is a measurement. With exact numbers, there's 2 different types, counts and conversion factors. Now, a count is simply as it sounds. You are counting how many students are in our chemistry class. Well, there's 24 students. There is no uncertainty with exact values. There either are 24 students or there are not. We're not questioning whether there's a student there or not. The same thing with conversion factors. Okay, conversion factors are also exact numbers. For instance, there's 1,000 millimeters in 1 meter. Okay, well, take a look at a meter stick. There's 1,000 millimeters in it. That's not a measurement. It's simply a conversion factor, so it's an exact number. So with any type of exact number, a count or a conversion factor, we would say that they have an unlimited number of significant figures because there is no uncertainty with that. Now when doing calculations, Whenever you're multiplying or dividing, your answer should always have the same number of significant figures as the smallest number of significant figures going into the problem. With addition and subtraction, you're not looking at the significant figures, you're looking to the places to the right of the decimal. The smallest number that goes into the problem to the right of the decimal are going to be how many you want in your answer. Here's a couple examples on that. The first one here is with our multiplication and division. So we've got 12.257 times 1.162. Now when you type that into your calculator, you're going to get an answer something like this, all these values after the decimal place. Now with multiplying and dividing, we want the number smallest of significant figures to be also the same in our answer. So with this, we've got 1, 2, 3, 4, 5 significant figures in this value, and 1, 2, 3, 4 significant figures in this value. So our answer then can only have 4 significant figures. Okay, this would be our smallest value. So when we look at our calculator, we would take 14.24. And this would be the rounded value. Now since 2 is below 5, we would leave it as 4. If this were above 5 or above, then we would round that up to 0.25. Now with the addition problem down here, when you're looking at addition, remember we're only looking to the smallest number to the right of the decimal place. So we've got something to the hundredths here, we're adding that to something to the thousandths place, and we're adding that to something from the tenths place. So our smallest to the right of the decimal is this one that only goes to the tenths place. So when you add all of these into your calculator, and this is what your answer comes out to be, 220.429, well then we know that we can really only be as precise as to go to the tenths place. So this would end up being 220.4. Finally, you're also going to need to be able to use scientific notation. Scientific notation is just a way to simplify things, especially for very large numbers or very small numbers. Now, the first part of a scientific notation is a value from 1 to 10. And the second part is going to be the power of 10, which is how many places that you would move the decimal point. So, for instance, in this first one, 5 times 10 to the negative 15th. This is just another way to write this big long number here. So this is a tiny value, 0.000. There's 15 places that you would have to move the decimal point over until you reach a whole number from 1 to 10. So 5 times 10 in the negative 15th, that's how many places I would move my decimal over to get this 5 by itself. Now this second example here, this is a very large number. So in this case, we're moving the decimal to the left, and if we move that decimal over to the left and keep moving it all the way until we get a value from 1 to 10, that would take 9 times moving that decimal. So this value would be 1 times 10 to the 9th. So you can see it's just a little bit easier to write it in this format as opposed to writing all those zeros in. A good rule of thumb is if you're getting larger than thousands or smaller than thousandths, you should really be using scientific notation.